Now let's see what happens if we have a block sliding along an incline and not along a horizontal surface. So we will have a block sliding down a frictionless incline at an angle of 18 degrees with the horizontal. We will determine the acceleration of the block. Let's start with the block on the horizontal table. In the previous two examples, I had a block here, here's the horizontal table. I had the vector for the gravitational force downwards, the normal force. I don't have a pulling force here, so I have removed that vector. I chose a coordinate system that goes along the table and perpendicular, so I have my XY coordinate system. In this example, however, the block is not going along a horizontal table, but actually on the incline. So what I can do is I can take this whole picture and tilt it to reflect the fact that the block is going to be sliding down the incline. The vector for the normal force is okay. Remember, the normal force is always perpendicular to the contact surface between the block and the bottom where the table is. So it is aligned still along the y-axis. The problem is, however, that my gravitational vector appears wrong. It's not pointing in the correct direction. So I actually have to adjust that vector. So I need to turn it down and shift it to the center of the block to account for the fact that gravity always points downwards towards the center of the Earth, and we always have to draw that vector applied at the center of the object. The next step is to actually look at the vectors and figure out what their components are. For the normal force, things are very easy because it's aligned along with the y-axis, so it has no x component, and I'll call it its y component plus Fn. Gravity, because I had to tilt it now, it's off the axis. So it's going to have x and y component, and I need to figure them out before I can actually go and write Newton's second law and the equations and solve the problem. So what are those x and y components for gravity? It's better to actually pull the gravity vector here on a separate diagram. I will keep my xy coordinate system still tilted at 18 degrees with the horizontal, and here's my vector g. It appears not to coincide with the origin of my coordinate system, but it's not a big deal. I can certainly shift my vector downwards to the origin, and I haven't really changed anything. Remember, vectors are not fixed in space. If I find the components of this vector g with origin at the origin of the coordinate system, that will be the components will be the same. It doesn't matter regardless of where the vector is located. So what I'm going to mark here is the angle between the vector g and the y component and the y-axis. The y-axis is simply the closer one, and that's why I chose that angle. And traditionally, a lot of examples always choose that side to mark the angle. Because of that, when I draw perpendicular from the tip of the vector to the y-axis, I will see that the adjacent side here in this little right triangle will turn out to be the y component of the gravitational force, and the opposite side will be the x component. So using the trigonometric definitions of sine and cosine, I'll see that the opposite side here, or gx, will be plus mg sine theta. Here I have used the fact that the magnitude of the gravitational vector is mg. And for the side that is adjacent to the angle theta in the right triangle, I will have mg cosine theta with a minus to reflect the fact that gravity points down into the right, which means it's in the opposite direction to my positive y. So what remains for me to determine is what's that angle theta here between the gravitational vector and the y-axis. I don't know that angle. What the problem tells me is that the incline makes an angle of 18 degrees with the horizontal. Let me mark it here at the bottom of the incline. You might guess that the angle theta will turn out to be the 18 degrees between the incline and the horizontal, but let's see why this is so. So here's one more diagram here, my third diagram. once again, the same coordinate system x, y tilted at 18 degrees. I have kept here the angle between the incline and the horizontal ground there at the bottom of the incline. Here is the right triangle between the gravitational vector and its x and y components. So the easiest way to see that this angle theta will be equal to the angle at the bottom of the incline is to actually draw this diagram on a piece of paper, and then take a pair of scissors and carve that triangle from your notebook. And then once you do it, you can actually rotate it and slide it directly into the angle here between the incline and the horizontal ground. Now, this is not just some like interesting and cute fact or coincidence. This is actually a geometrical fact, and in geometry you will see that any two angles with mutually perpendicular sides will either be equal or supplementary. And what I mean by mutually perpendicular sides is that here I use the fact that the left side of my angle theta is makes a perpendicular with the left side of the angle here at the bottom of the incline. The right side of theta makes a perpendicular with the right side of the angle at the bottom of the incline. So truly those two angles are with mutually perpendicular sides. Anyway, if you don't feel very confident in your geometric skills, not to worry. All you need to remember here in physics is that the angle between the gravity vector and the y-axis will always be equal to the angle at the bottom between the incline and the horizontal. So if you just memorize that fact, you can actually skip the geometrical proof and just continue with the solution of the problem. So let's see what we have so far. We tilted our coordinate system to reflect the movement of the block down the incline. We looked at the components, and we saw that we need to work with the x and the y component of the gravitational force. We chose an angle theta that happened to be equal to the slope of the incline, or the direction between the incline and the horizontal ground. And our problem here is 18 degrees. And with that, the choice of angle theta between the gravitational vector and the y-axis, we found out that the x component will be mg sine theta and the y component will be minus mg cosine theta. Now I'm finally ready to look at Newton's second law and start writing down my equations of motion. Remember, even though Newton's second law in vector form is simply F net is equal to ma, we always work with its component form. So starting with the x components, now I have to add all the x components. I don't have many forces here, so the only force here that has non-zero x component will be gravity. And for completeness here, I added the x component of the normal force, but that is 0. So my equation here becomes mg sine theta plus 0 is equal to m times the x component of the acceleration. Notice here that we actually canceled the mass. In other words, we can divide out the mass from both sides of the equation, which is very fortunate because the problem did not actually give us the mass of the block. And that's why many problems of incline is when there's no friction involved and the questions are about acceleration, you will find out that the problems will actually omit to give you the mass of the block. So with that, we can actually see that the x component of the acceleration is going to be equal to g sine theta. We can even plug in here the numeric values for g, 9.8 meters per second squared, and then we have sine of 18, which is the angle between the incline and the horizontal, which will give us for the x component to be 3.028 meters per second squared. This is where normally the problem ends, the solution. We claim this is the acceleration and we are done, and you can do that certainly if you're doing a test, a quiz, or homework. But let's see what happens with the y component of the acceleration. For that, we'll have to look at the equation for the y component. So I have to add all the y components here. Both gravity and the normal force have non-zero y components. It will look like minus mg cosine theta for the gravity That's the y component of gravity plus the y component of the normal force, which I called it Fn. And that whole thing has to be equal to the mass times the y component of the acceleration. Remember here, for blocks that are sliding, regardless of whether they're sliding along a horizontal surface or an incline, we can have the normal force or the y component of the acceleration, but never both at the same time. So in this case, it's pretty obvious that the block is going to maintain contact with the incline, and therefore we will have a normal force to account for that interaction. And we will have no y component of the acceleration. In plain words, what this means is that the block moves smoothly down the incline. There are no bumps, and it's not like jumping off the incline. The y equation then becomes minus mg cosine theta plus Fn is equal to 0, and that y equation actually can give me the answer for the normal force in this case if someone were to give me the mass of the block. But as it stands, the problem is about the acceleration and I don't know the mass, so I can actually combine my result for the x component and the y component of the acceleration for my final answer. The magnitude of the acceleration will be 3.03. I have rounded here to our standard 3 digits, and the direction will be down the slope or down the incline.